Hello and welcome to our Lunch and Learn session on Graph Analytics with ArangoDB. ArangoDB, just in case you haven't been working with that before, is a scalable graph database which actually combines several other specialized data models such as document, key value, and graph into one database engine, into one query language. So you actually don't have to switch between different specialized database systems. I'm Jörg. I'm the head of engineering and machine learning here at ArangoDB, and I'm excited to share some aspects of graph analytics with you today. So what is graph analytics actually? So if we look at analytics, so analytics take care of the discovery, interpretation, and communication of meaningful patterns in data. And so if we just look at what graph analytics then probably means, this is actually the same just in the context of graph data. And that actually allows us to answer like a lot of different and interesting questions from our graph structures. So for example, community detection, where are there separate sub-communities within a larger graph? Recommendations, so for example, we'll have an example of product recommendations later in this lunch and learn session. Centrality in your graph, which are central nodes? So for example, in the social network, which are your influencers? Path finding, how can I get from A to B, potentially in the fastest or most efficient way? Fraud detection, permission management, and there are many more different use cases for graph analytics. So let's get started by actually talking about some graph algorithms which can already help you to achieve some of those goals. So if we look at what kind of graph algorithms are out there, so first of all, probably we are all aware of like search and traversal, which means we want to find a particular node or edge within our graph. And their breadth first search or depth first search, they're probably the best known ones out there. Secondly, there's a group of algorithms for path finding. How can I get from A to B, potentially on a weighted graph? So I have like little numbers on my edges telling me how long it takes to get from A to B, or in general, how expensive is it to get from A to B. Centrality, as mentioned, this is concerned with what are the most important nodes in this network. Cycle detection, we want to identify different cycles within our graph where we can go like within a circle and reach back in the same node. And this, for example, is important in make files, or if I have like a dependency graph of tasks out there. And last but not least, community detection, as mentioned here, we are concerned about identifying separate sub-communities within our larger graph. So just to get deeper into one of those examples, let's take a look at centrality. And centrality is rather interesting because it can actually mean different things depending on your context. So probably the most simple measure of centrality would be degree centrality, simply how many in and outgoing connections does a node have. And in that case, if you take a look here, our blue node, that is actually the one with the most connections. So if we just measure degree centrality, that would be our most central node. Another measure would be closeness centrality. So that is kind of the average closeness to all nodes. So how long does it get me on average to get to all the other nodes? And here we actually have multiple nodes which have the same like smallest closeness to all other nodes, and those are the green nodes in our graph. Feel free to actually just count that yourself. How long does it get to all the other nodes from here? Furthermore, we got betweenness centrality. So this is how often is a node actually connecting different subgroups. So like how if you have different subcommunity, different subgroups, you can imagine like this would be a connecting node connecting like multiple independent parts or more or less independent parts of your overall graph. And that can just be easily measured by how often is a node on the shortest path. And here on the right, this is easily visible. If you take a look at the purple node here, if that node would be gone, the graph would actually scatter into two separate subgraphs. And then last but not least, we got PageRank. So that's kind of the original Google algorithms for identifying the importance of different websites, and that's actually the transitive influence, and we'll look at that in a bit later during this session. But first, just like one more common day example of graph analytics, and that would be collaborative filtering. Probably all of you have seen something similar to that, where like customers who bought this item also bought this item. So basically you get a product recommendation based on your previous rating or purchase behavior. And we can actually take a short look how we can leverage that for movie recommendations, especially in these days, given the isolations. Let's actually take a look at what movies we might want to watch but haven't watched yet. And so for that, there's actually a nice data set out there from IMDb, so movie rating. And if we look at that, we can actually model that as a graph. So on the one hand, we get user information, and then a particular user rates a movie. So this is already a very simple, in that case, directed graph. And we can leverage that for getting movie recommendations out of this. And so to get started with that, let's take a look what it would take to find movies I personally like. So the first step would be we identify like us as a user in that graph, that node. And from there, we want to find all the movies we really enjoyed ourselves. So the ones we rated with 5 stars, giving us a set of movies. And then we actually, the next step is we want to identify people with a similar movie behavior, a movie preference as us. So we want to identify people who actually also rated those same movies with 5 stars. So the same ones we like, they also rated. And then we have a set of users which supposedly at least has a similar taste as we do. And so then from those users, we can go back and see like which other movies did they rate very highly, and which we haven't seen yet. So that will give us a movie recommendations by people who have similar tastes as us, and we can go on watching new movies. The cool thing, and this is just kind of like an outlook, is we actually have also interactive notebooks with that. I'll talk a little bit about the workshop. You can just go through also for free here, but I just want to show you one particular example here. So those are interactive notebooks. You don't have to install anything. You can just run all those cells. I won't do that now for time reasons, but that will actually allow you to experience this movie example and just build it by yourself. But more to that later. Okay. As mentioned, we also got PageRank out there. So PageRank, as already mentioned, is this original Google algorithms where we go in and try to identify like which are important or like central, in that case, nodes in our website graph. So the website graph is basically formed by nodes and sites linking to each other. So here, for example, like the red side down here is linking to the yellow side up here. And then the idea of PageRank or also other algorithms going in this transitive centrality is the more influenced I get from nodes pointing to me. So it's basically, it's the importance is flowing in this graph, the more important I'm myself. So if we look at that, for example, here, our happy yellow node, why is it so big and why is it so important? It's actually because it has a lot of nodes pointing to it. So we have a lot of incoming links in that case, and that actually makes us important because we have a lot of importance flowing through from like a lot of smaller, less central nodes to us, but in some this actually aggregates to an important number. Then as another example, if we look at this red node here in the upper right corner, that actually has just one incoming link. But this incoming link is from one very important node, the yellow node we just discussed. And hence, we are actually also expect this node is rather important because it gets the incoming link from another very important node. This is what's meant by transitive centrality. It's kind of like flowing and it's being linked from an important one, we assume it's important as well. The interesting aspect is that we can view PageRank also as the chance that a random server would land on our website. So imagine you're just like someone sitting in front of your computer and just randomly you click on links on websites, and then after a certain amount you just stop surfing. And so the question is like, on which website did you land? And so if we look at that, then the size of our bubbles or the centrality of our nodes here actually corresponds to the likelihood here. So if we, for example, start here on with this node, we end up here, we go back. So it's very likely that we'll be stuck in the circle. Also, like here is this blue node in the middle. We don't have that many incoming nodes, but it's like we have actually many incoming nodes, but less important ones. So we are actually also pretty important. So the system by which we can implement something like Pregel in a very scalable fashion. So the challenge here is, if you look at Google, you won't fit all of those websites onto like a single machine, even if it's like a really big computer. So we actually need to distribute the computation of such graph. And here, there's actually a system developed by Google for that, and it's open source. And for example, ArangoDB implements it as well. And that is called Pregel. And it's designed to be like a large scale graph processing framework. And how it does that is by dividing the computation into super steps. So in each super step, all the different worker nodes in our cluster can first do independent work, identify, recompute their centrality, and then they send messages to all neighboring nodes. So in our graph, basically like step 1, each node would kind of compute its own importance and then send an update to like all neighbors. So here, for example, blue node sends an update here, update here, update here. And then we have a barrier where we basically sync. And then in the next super step, based on all incoming messages, we recompute our own importance, our own centrality, and send messages again to all our neighbors, and so on and so on. And so we basically run that either for a predefined number of steps or until it converges. So basically until our graph doesn't change anymore. And ArangoDB has supported Pregel for a long time. There are a large number of predefined algorithms in there you can just leverage out of the box, as for example, PageRank and many others. And just recently, we also introduced a new custom Pregel feature, which still is experimental, but feel free to try that out. And that actually allows you to specify your own Pregel algorithms on the fly. So previously you would have had to go in and actually write C++ code, restart your ArangoDB instance. But here with that project, you can actually run that on the fly and also change or add new algorithms for running cluster. So as mentioned earlier, this is actually based on a workshop we did 2 weeks ago, which also has more material and has more of those interactive exercises I briefly showed in the middle with the Jupyter/Colab notebooks. So if you're interested in learning more about graph analytics with ArangoDB, I would highly recommend you to try out this workshop. It will give you even deeper insights than we can cover in this short lunch break session. So maybe it's then not a lunch session, the workshop, but that would be something you can spend afternoon on. So it roughly takes probably around 2 hours to go through that. Otherwise, thanks so much for listening. If you're interested, as said, check out the Graph Analytics workshop. If you're just interested in trying out ArangoDB, you can take our managed service ArangoDB Oasis, or otherwise feel free to contribute to our open source community, either on Slack, GitHub, or at many other channels. Would love to hear from you. Thank you so much for listening.